Solve the following logarithmic equation. So before we get to this equation, I want to take a minute to look at a few methods of solving logarithmic equations. One method is to convert your logarithmic equation into an exponential equation. So you start off with something in this format here, y equals log base b of x. The base of the log is the base of the exponent. The log always equals the exponent, which is y, and what's inside the log is what the exponential expression equals. The other method that's used often is sometimes called the one-to-one property of logarithms, and sometimes it's called the property of equality. In this method, you have to have log with the same base on both sides of the equation. Log base b on one side, log base b on the other side. And because logarithms are one-to-one functions, what's inside those logarithms have to equal each other. So you have the expression inside the log on the left being u, the expression inside the log on the right being v, and those have to equal each other. It allows you to get rid of the logs in the equation. For this example, I can see I have log of 8x plus 10 equals 1 plus log of x minus 4. I do have log, and no base is specified, so that means this is base 10 on both the left and the right side, but because of this plus 1 here, I'm not going to be able to use that one-to-one property or property of equality. So instead, I'd like to use the method of converting to an exponential. But in order to make this work, I need to have a single log on one side of the equation. So I'm going to do a little bit of rearranging to start off. I'm going to subtract log of x minus 4 on both sides of the equation. That leaves a 1 on the right. On the left, I have log of 8x plus 1 minus log of x minus 1. Now I'm going to be able to condense these two logs into a single log because they have the same base of 10, or sometimes it's called the common log. Now because it has subtraction, we're going to condense this using what's called the quotient rule. So that gives me log of 8x plus 1 over x minus 1 equals 1. So just to take a moment to clarify that quotient rule, this expression inside the log goes in the numerator because this log is positive, and the expression inside this log went in the denominator because that log was negative. And now that I've got a single log on one side of the equation, I can convert this to an exponential. I'm going to use a base of 10 because no base was specified. The exponent is the 1, and this equals the expression inside the log, which is 8x plus 1 over x minus 1. So 10 to the first power is 10. I can multiply both sides by the denominator to clear fractions. That gives me 10x minus 10 when I use the distributive property. And on the right-hand side, those denominators canceled out, leaving me with 8x plus 1. I want to get all the x's onto the same side, so I subtract 8x. That's 2x minus 10 equals 1. Now that I've got x, all the x's on one side, I'll get x by itself. I'm going to add 10 to both sides. That's 2x equals 11. Divide both sides by 2, and I have x equals 11 over 2. Now, with every log equation, you should check to make sure that you don't have any solutions that wouldn't work in the original equation. So I'm going to check x equals 11 over 2. In the original, log of 8 times 11 over 2 plus 1 equals 1 plus log of 11 over 2 minus 4. Now what we're checking for is to make sure that we're taking the log of a positive. Log of a negative is undefined and log of 0 is undefined. So here I've got a positive times a positive plus a positive, so this expression will be positive and that's okay. But over here we have log of 11 over 2 minus 4. 11 over 2, let's see, 2 goes into 11 5 times with 1 left over, so that's 5.5. So 5.5 minus 4 is also a positive, and so we're going to be able to keep that solution of 11 over 2. So the solution to the equation log of 8x plus 1 equals 1 plus log of x minus 4 is 11 over 2. What rate of interest compounded annually is required to triple an investment in 28 years? So first I want to start off with this piece of information in the problem, that our interest is compounded annually. So that tells me what formula to use. I'm going to use the formula A equals P times 1 plus R over N to the NT. Let's take a moment to make sure we understand all the pieces of this formula. So P stands for the principal. Which is our initial amount of money. Initial or starting amount. R is your interest rate, your annual interest rate. T is for time in years. N is the number of compoundings in 1 year. Compoundings refer to how often interest is added into the account. Most savings accounts would add interest monthly, and N would be 12 for 12 months in a year. Or some accounts could be quarterly. In that case, N would be 4 because interest would be added or compounded 4 times in a year. In this example, it says compounded annually, so our N will be 1, once a year. And then finally we have A. A is our accrued amount or our ending amount. The amount after a certain time period. So in this problem it says what rate of interest, so that means R is our unknown that we're trying to find. I already mentioned that it says compounded annually, which tells us that N is 1, is required to triple the investment. That's going to be important in just a minute. Triple in 28 years. So T is 28. Now for tripling the investment, that's telling you the relationship between your principal, your initial investment, and A, your accrued amount. So because we're trying to triple the investment, A will be equal to 3 times P. Triple the principal is what we're trying to achieve. Now with all this information, we should be able to substitute values into our formula and solve for our unknown R. So let's start with our formula. A equals P times 1 plus R over N to the NT. A is 3P, we're trying to triple our investment. P, 1 plus R is our unknown. N, the number of compoundings is 1. And 28 in for time. So we're going to solve this. First, let me do a little bit of cleanup. R over 1 is the same thing as R. And 1 times 28 is 28. Now to solve this, I can divide both sides by P. That's going to cancel out the P on both sides, leaving me with 3. On the right, I'll have 1 plus R to the 28th. Now to solve this, I could take the 28th root of both sides. The 28th root and the 28th power will cancel each other out, leaving me with 1 plus R on the right. And then I can get R by itself by subtracting 1 on both sides. So R is equal to the 28th root of 3 minus 1. Let's type that in the calculator to get a decimal approximation. So to type the 28th root, I'm going to rewrite this as 3 to the 1 over 28 minus 1. So you can write radical expressions as exponents. So I have 3 to the 1 over 28 power minus 1, and our rate is 0.0400, and we typically write these rates in percentage form, so I'll move the decimal point 2 places to the right to get 4%. So we would need a 4% interest rate to triple our money in 28 years. If Tanisha has $100 to invest at 5% per annum, compounded quarterly, how long will it take before she has $150? If compounding is continuous, how long will it be? So let me point out a couple things, keywords. We've got compounded quarterly, and compounded quarterly indicates that we're going to be using a formula A equals P times 1 plus R over N to the NT. That's the compound interest formula. But then in the second part of the question it says if the compounding is continuous, that's an indication of using a different formula, which is A equals P e to the RT. So in the first part, we'll use our compound interest formula, and in the second part, we're going to use the compounded continuous formula. Both formulas use most of the same variables, so let's take a minute and make sure we know what each of those variables stand for. We have P being the principal or initial amount of money. We have R as our interest rate. We have a T for time. We have n, which is the number of compoundings in a year. We have A as our accrued amount or ending amount. And this value right here of E is not a variable, E is a number, and that number is approximately 2.718. It is irrational, it continues on forever. The decimal values continue on forever without any pattern. So let's focus on the first part. Tanisha has $100. That is our principal. She's going to invest at 5% per annum is per year. So our rate is 5%, and we typically write that in decimal form. So you would move the decimal place 2 places to the left. The question says how long, so that's our time being our unknown, and how long before she has $150. That $150 is her accrued amount or ending amount. So we're going to be able to substitute these values into the compound interest equation and solve for the value of time. There's actually one more variable that we need to notice, and right here it says compounded quarterly. Compounded quarterly is going to tell us the value of n. Interest is compounded quarterly, which will be 4 times per year. So we're going to substitute these values into the formula. A equals P times 1 plus R over N to the NT. A, our accrued amount, is $150. Our principal, our initial amount, is $100. We have an interest rate of 5%, compounded quarterly, so N is 4. And our time is the unknown in this equation. So we're going to solve this equation by first getting rid of the principal here. What we're trying to do is to isolate this exponential onto one side. So we've got to get rid of that 100 by dividing both sides by 100. That leaves me with 1 plus 0.05 over 4 to the 4t. And this side, they have a common factor of 10, so that would reduce to 15 over 10. I can reduce that even more. 5 goes into both of those, so that's 3 over 2. And let me use my calculator to simplify this decimal. That's 1 plus 0.05 over 4. And so we have our base being 1.0125, and that's all to the 4t. We can continue to solve this exponential equation by taking the log of both sides. So I'm taking the log on the left and the log on the right. And once you introduce the logarithm, you can now use the power rule to move this exponent out in front of the log. So that's going to give me natural log of 3 over 2 equals 4t natural log of 1.0125. And now you can get t by itself by dividing both sides by 4 natural log of 1.0125. That's going to cancel the 4's and cancel the natural log, leaving me with t by itself on one side. And I have natural log of 3/2 over 4 natural log of 1.0125. Let me put that in my calculator. So in my calculator, I'll type natural log of 3/2 divided by, I need parentheses for my whole denominator, so that's 4 natural log 1.0125. Close parentheses for the log, close parentheses for the denominator. And I have that it takes approximately let's round to 2 decimal places, 8.16 years for my $100 to grow to $150 with 5% interest compounded quarterly. So now we want to do the second part of the problem, which if you remember was that we want our interest to compound continuously, and when interest is compounded continuously, we'll use the formula A equals P e to the RT. So let's take a look at that. So if we use A equals P e to the RT, if you remember, our accrued amount was $150. We had an initial amount of $100. Our interest rate was 5%, and we were solving for time. So we're going to start solving this much like we solved the other, using the other formula. We want to isolate the exponential, so we've got to get rid of our coefficient by dividing by 100 on both sides. That reduces down to 3/2. The 100s cancel from the right. Then we'll take the log of both sides. I'm using natural log. We can use the power rule to bring our exponent in front of the log, or that's multiplication when we bring it in front. Natural log of e is 1. One times 0.05t is 0.05t. And then we would divide both sides by 0.05. Giving me natural log of 3/2 over 0.05. Now we'll type that in our calculator. Natural log 3/2 divided by 0.05 gives me 8.11. So it would take approximately 8.11 years for our $100 to grow to $150 if our interest is compounded continuously. So I just want to compare that to our previous answer. You can see that compounding continuously takes a little bit less time for that money to grow than compounded quarterly. The size p of a certain insect population at time t in days obeys the function p of t equals 800 e to the 0.04 t. In part A, we want to determine the number of insects at t equals 0 days. At t equals 0 days, we're going to use our function p of t equals 800 e to the 0.04 t. If t is 0 for 0 days, we'll substitute a 0 in for time and get 800 e to the 0.04 times 0. That's 800 e to the 0, because 0.04 times 0 is 0. E to the 0 is 1, and 800 times 1 is 800. So the initial population of insects, or the number of insects at t equals 0 days, is 800. In part B, it says, what is the growth rate for the insect population? And the growth rate, which we usually call K, is going to be 4%. So our K is 0.04, or 4%. That is our growth rate. In the next part, it says use a graphing utility to graph the function. Let's take a look at our calculator. In the y equals menu, I would graph the function 800 e to the 0.04, and I'll use x instead of t. You can take a look at the graph. And the reason why we're not seeing anything is because our initial amount is 800, so we're not really seeing a good picture. So what I like to do is take a look at the table of values, and you can see with my values around -2, my y values are in the 700 range. We know when we get to 0, the y value is going to be 800. So I really need to adjust my y scale. For my y scale, let's adjust it to be starting at, maybe starting at 0. And let's go up to 1,000 for now, but we might adjust it again. So now we can see that curve, and because I'm not seeing the increase on the right here, I'm going to go even higher. Let's go to, let's say 3,000. Okay, so now we're kind of seeing the full picture of the graph. And let's explore what the next part says. And it says, what is the population after 10 days? Here, population after 10 days. There are a few ways that we can work this out. We can do just like we did here, population at 0 days, where we substitute 10 into the equation. That's 800 e to the 0.04 times 10. We can type that in our calculator. That's 800 e to the 0.04 times 10. Don't need that parenthesis there. And after 10 days, our insect population grows to 1,193. Now another option, if I go to the graph, is to use a feature in the calc menu. So I'm going to hit second and then trace. That pulls up the calc menu. And number 1 is value. This allows me to type in an x value of 10, and it's going to tell me what the y value is. 1,193. Okay, let's see what the next part says. The next part says, when will the insect population reach 1,200? Okay, so what I'm going to do is substitute 1,200 in for P of t. P of t is the population after time. And then solve for t. So I would divide both sides by 800. The 800s cancel from the right. On the left, this reduces to 12 over 8. Can reduce a little bit more. So 4 goes into 12 3 times, 4 goes into 8 2 times. I can then take the natural log of both sides. Once I've done the natural log, I can use the power rule to bring that power in front of the log. That gives me natural log 3 over 2 equals 0.04 t. Natural log e. Natural log e is 1. So we have 0.04 t equals natural log 3 over 2. And I can divide both sides by 0.04 to get t equals natural log 3/2 over 0.04. So I'll type that in my calculator to get a decimal value. That's natural log 3 over 2 divided by 0.04. And now I have 10.13, let's round to 7 there. So the insect population will grow to 1,200 after 10.137 days. There's another way to get that. We can use the intersect feature in the calculator. That's also in the calc menu. So I would go to Second, Calc. Oh, I need to do something first. Give me just a second. So in the y equals menu, I need to type in that 1200 that we were trying to go to. So there's the 1200, and on the graph, that intersection point is the number of, that's going to give us the number of days. So now I go into that calc menu. I'm going to select number 5 for intersect. It asks me first curve, I hit enter, second curve, I hit enter, and then it says to guess. You want to move your cursor closer to that intersection point. And you can see our x is getting closer to that value of 10 there. And we get the same 10.137 from our calculator. I believe there's one more part, so let's take a look at that. When will the insect population double? So we're still looking for time on this part. So we know we started off with an initial population of insects of 800. Double that 800 would get me to 1600. So that's what I need to substitute into my equation. 1600 for the P of t, population after time, equals 800 e to the 0.04 t. I'm going to solve this just like I solved the other one that we just did. I would divide both sides by 800. 1600 over 800 is 2. The 800s cancel on the right, giving me e to the 0.04 t. Then I would take the natural log of both sides to solve that exponential equation. I would use the power rule to bring that 0.04 t out of the exponent. Natural log of e is 1, leaving me with 0.04 t equals natural log 2, and then I would divide both sides by 0.04. t equals natural log of 2 over 0.04. And then I'll type this in my calculator. So natural log 2 over 0.04 would give me 17.329 if I round. So it would take 17.329 days for the insect population to double from 800 to 1600. We could also get this in our calculators, making that value 1600. And if you look at this picture, you can see that I don't see the intersection point. So I'll have to adjust my window a little bit more. So let's change it to 20. And now you can see that intersection point. So I hit second and trace to go into the calc menu, select number 5, hit enter for the first curve, hit enter for the second curve, and I want to guess, move your cursor closer to that intersection point to guess. If you only have one intersection point, you can actually skip this step, but if your graphs have more than one intersection point, you need to move close to that intersection point. So you can see here we got 17.329, just like we did by calculating it by hand. The population of a southern city follows the exponential law. If the population doubled in size over 28 months, and the current population is 40,000, what will the population be 3 years from now? So the exponential law that we're referring to is our exponential growth and decay model. And that is following the formula A of t equals A naught e to the kt. And sometimes instead of A, we use P for population. So you might see P of t equals P naught e to the kt. So let's talk about what these different pieces of the formula mean. We have that P naught, which is our initial population. And if you're using the formula with A, that would be A naught. The K is your growth or decay rate. So it's called a growth rate if your population is growing. And your value of K will be positive if your population is growing. And it's called decay rate if your population is getting smaller. And that value of K will be negative if your population is getting smaller. Then we have T, which is our time. And we can use any unit of time, months, days, years, whatever suits our problem. And then we have our P of t, and that's going to be the population after time. And that would be also, if you're using the A's, A of t. So that's going to be the amount you have after a certain period of time. So in order for us to answer this question, we really need the growth rate. We need the value of K to be able to answer this question about what will the population be 3 years from now. So we're going to be able to find the growth rate with just this piece of information in the beginning about the population doubling in size over 28 months. So the 28 months is a time, and the population doubling in size tells me the relationship between P0 and P. So P will be twice P0 for the population to double in size. So with that information, we're going to be able to substitute into the formula and solve for K, the growth rate. So let's do that. So we have our formula, P of t equals P0 e to the kt. And with just using this two pieces of information about 28 months and the population doubling, I would be able to substitute 2 times P0 in for P, leave P0 here, and substitute a 28 in for time. That was 28 months. The population doubled in size in 28 months. Then I can start solving by dividing both sides by P0. And you can see that that P0 cancels out on both sides of the equation to give me 2 equals e to the 28k. Then I'll solve this exponential equation by taking the log of both sides. Then I can use the power rule, and the power rule allows me to move that power in front of the log to make this natural log 2 equals 28k natural log e. Natural log e is 1. And I'll divide both sides by 28 to get k equals natural log 2 over 28. I could put that in my calculator to get the growth rate, but I don't want to do any rounding in this. K is going to be a decimal answer, and those decimals will go on forever. So I don't want to round at this point. I want to round at the end of the problem. So I'm going to leave k in its exact form, which is this natural log of 2 over 28. So let's go back to the question. And the question says, the current population is 40,000. What will the population be 3 years from now? So with my formula was P of t equals P0 e to the kt, but I was able to find what k was. That's natural log 2 over 28. So now when I'm using this formula, I have two variables. I have P0, which is my initial population, and the time. And that's exactly what they gave me on this second part of the question. Their current population is 40,000. What will the population be 3 years from now? 40,000 is the initial population. 3 years from now is the time. So I'm going to use, for P0, I'm going to use 40,000. And for the time, I have to be careful here because although I told you earlier, for time you can use any units, days, months, years. You can use any units, but you have to be consistent about whatever units you're using. So because we used 28 months earlier, we need to make sure the units for our time is months. So 3 years is the same thing as 36 months. So we got that by doing 3 times 12, the number of months in a year. So I can substitute 40,000 and a time of 36 months to find out what the population will be 3 years from now. So I'm going to put this in my calculator. 40,000 E. It's a little bit easier if I type the 36 first instead of last. Natural log 2 over 28. And that's 97,521, and I'll round to the nearest whole number. And I just want to make a quick correction just in case this confused anybody. This is natural log of 2 over 28. I didn't want anybody to think that 28 was inside the log. Okay, so after 3 years, our population grew from 40,000 to 97,521.